To start this chapter on dynamical systems, let's take a look at an experiment that some colleagues from Lille University did a couple of years ago, where they looked at a CO2 laser. So you have two mirrors, and in between is CO2 gas, and then light oscillates back and forth, gets amplified by the CO2 gas, and then in the end you get laser action. Now, what these people added to the mix was this rectangle here. So what's this mysterious rectangle doing? Well, it's an absorber, and moreover, they were able to hook up this absorber to some sort of outside voltage source such that they could modulate the absorption that was happening inside the laser cavity. And the voltage they put over the absorber had the following form. You first had a DC offset, A, and then on top of that DC offset, you had a small modulation of this form here, so sinusoidal modulation with frequency omega. They swept the DC offset in their experiments, and they swept this from 60 to 460 volts. And then the modulation here, that was very small in comparison, that only had an amplitude of 3 volts. Now for the resonance frequency, they happened to pick 640 kilohertz. Why? Because they've seen in their experiments that coincided to some sort of resonance phenomena that was going on in their system. Okay, so this was the setup they had. And then they did the following experiment. They varied this DC offset A, and what they did is they sampled the output of this laser here with the same frequency here, 640 kilohertz. So they just measured the output of the laser only once per period, and then they recorded that for different values of A. Let's first focus our attention on very small values of A. So if you don't drive the system very hard. What do you think will happen then if you sample the output once per period? So think about this for a while and try to imagine how many different values of possible samples that you could get in this case. So if you don't drive the system very hard for small values of A, that basically means that you have a linear system. And for linear systems, you expect, if you drive them with a certain frequency omega at the input, that the output will also vary with exactly the same frequency, because linear systems, they don't generate new frequencies. So if we draw this, for example, as a function of time for the voltage over here, we know that our voltage has an average value of A. And on top of that, we have some sort of oscillation going on with a certain frequency. Okay. And then if you now plot the output of the system as a function of t, so the output is the power. Power also averages around a certain value here. And let's just assume that if we increase the voltage, that the power goes down because the absorber gets to do more work. But basically, since we do not expect to generate new frequencies in the system, we have a system that, and my drawing is not very accurate, so that has exactly the same frequency at the output as it has at the input. Now, if we sample this output signal P with exactly the same frequency as the input, so we just sample once per period, so for example over here and over there and again over there, since this has exactly the same value in each of these periods, we just get a single value of this sampling procedure every time the same over here. Okay, so far so good, so far so linear. But now what they did is they increased the value of A, and then at some point they realized that their sampling procedure did not only give a single value, but actually gave two values. So think about what this could mean in terms of the shape of the output curve in that case. So pause the video and try to figure out a possible waveform that could give two samples per output value. Okay, so now we have a nonlinear situation because all of a sudden we have two samples that we get with this procedure. And if we get two samples, this means that our shape here should be drastically different of the output. So for example, I'm just measuring something, we get something like this. Okay. So you might have observed that now in this case, the period is twice as long as what we had before. And this can indeed explain why we get now two possible values if we do this sampling procedure. So for example, we get a sampling point over here, right? And then for the next sampling point, which in the linear case would have given the same value, now all of a sudden we get a different value. But then here, from the next period on, the cycle repeats. So in this particular case, we see that we have indeed two possible values for that sampling procedure. This phenomenon here is called period doubling, for obvious reasons, because the period in this case is twice as big. And we actually have generated a subharmonic of the system with twice the frequency. So this is a hallmark of a nonlinear system where input frequencies give rise to different output frequencies. And actually, what turns out to be the case, if you keep on increasing the value of A, then this period doubling happens once more, and all of a sudden you have 4 different values, or even 8 or 16, or sometimes it can get even very, very messy. So if we look at the actual experiment that people did, so this is the way they hooked up their oscilloscopes. On this horizontal axis, they had this offset A, the DC offset A, and here on the vertical axis, they had the different points that they sampled. So you see in this initial region over here, they just had a single sample per bit periods. Then at a certain point, once they crossed this threshold over here, which is a very important situation here, then they ended up in a situation where you have these 2 samples. You can clearly see the 2 samples per bit over there. And then you see if you keep on increasing A, excuse me, then you see that this period doubling keeps on happening. And in the middle here, you have a very complicated regime where there's many different branches. It's even very complicated to tell them apart. But then after a while, things quieten down again, and you get back eventually to a single solution at the end. The interesting thing here also is that the equations that describe this system are actually very simple looking. They're not hugely complicated equations with dozens of different terms and things like that. No, they're actually quite simple equations. They are nonlinear, but it turns out that even these very simple nonlinear equations, they're enough to give rise to this very complicated sets of dynamical behavior. And these are the things that we will be studying in this chapter in different situations, starting in one dimension and then moving on to higher dimensions, looking at discrete systems, but also looking at continuous systems. But this was just an example to illustrate that dynamical systems are everywhere, and it's very interesting to be able to study their dynamics and to see how they behave in different regimes depending on some sort of external parameter.